physics. We're here in medieval times with these bozos. And today, we're going to be firing this with that. No, not with Trey. With that.
So Chris, what are we doing?
We're doing stuff. We're going to take this hammer.
Yeah?
And we're going to do some stuff with this hammer.
A trebuchet is a large siege engine, often used during the Middle Ages for raiding castles. The machine uses a large counterweight to fire projectiles long distances. They have sometimes been known to wear pants.
Okay, so if this thing would wear pants, would it wear them like this?
Stop.
Or like this?
Stop.
With a successful plan in place, I took over 15 minutes staring at the camera, but then we started building.
Trebuchets are better than catapults because catapults are stupid.
We worked day and night through wind, cold, rain, cold, and even snow. In total, it took about 15 hours to build and assemble the trebuchet.
We use the equations force equals mass times acceleration and torque equals force times lever arm. We combine that. If you look at our diagram here for a 2-foot piece of arm, we calculated its torque for our counterweight right here. And the 2-foot piece of arm, we got that number right here.
Alright, and then for the throwing arm, we calculated the torque of the bottle and added that to the weight of the 7-foot piece of arm torque, and we got this number. And then we subtracted both numbers and got around 269,000 Newton meters.
We combined these two equations in order to get this. We plugged in all of our work, as you see here, to get 7.071 radians per second squared as our angular acceleration. And then we found our displacement, our angular displacement, to be at 1.3 radians. Then we used this equation right here to solve for our final angular velocity, and then used our angular velocity to solve for our initial launch velocity.
After finding the initial velocity in the x and y direction, our initial displacement, and the acceleration due to gravity, we used this motion equation to create this displacement over time graph, and found that the amount of time the projectile would be in the air for to be just over 3 seconds. We then used this other motion equation down here to calculate the displacement in the x, or how far the projectile would travel forward. We determined that distance to be just exactly to 134 feet.
Okay,
This is the back piece, that's not fair.
we all did it.
Actually,
Yeah. There's actually stuff on it that keeps it from moving.
Well,
Okay.
yeah.
That's what we were trying to avoid. I'm glad we caught that on camera.
No, wait, shoot. 3 3/4.
3 3/4.
Quarters.
Quarters.
3 3/4 is where.
Screw it.
As you can't see, we are now working in the dark.
Let's see here. We get a lot of time. That's not 30. That's not. What's the?
Why don't you just draw? Or is it square root of 2 over 2?
It's square root of 2 over 2, I think.
So